What's that I hear you saying? You love college algebra so much you can't get enough? You can't fall asleep unless you hear someone droning on about equations? Well, do I have a treat for you. There were a couple of fun topics in the section on logarithms and exponents that we didn't have time to cover during our regular lectures. So today I'd like to teach you a couple of special exponential models. They're called the logistic function and Newton's law of cooling. Let's jump right in. A few days ago in class, we modeled the population of California with this equation. It was P of t, a population as a function of time, was 34 e to the power of 0.009263 t. And this was a very good model for a while. We found out that this matched the idea that in the year 2000, there were 34 million people. In the year 2010, when t equals 10, so P of 0 was 34 like we wanted. P of 10 was 37.3 like the problem told us. That's how we derived this model. And we were even able to predict the population this year, P of 20. My model said it was 40.4. In reality, it's 39.7, so we were off by a little bit, but we did pretty well. Now, this seems reasonable. The population of California is going to grow as a proportion of the number of people who are already living there, like this nice gentle exponential sloping curve. It's slowly accelerating upwards. And in the short run, that seems reasonable. Yeah, the number of people born is a function of how many people already live in the state, because the people who already live in the state are the ones who are having babies. But there's a problem with this model, and that's that if we zoom out, far enough, this curve gets very, very steep indeed. As a matter of fact, in the year 3000, that's 1,000 years after that's 1,000 years after the new millennium. If I plug in 1,000, this is going to be 34 e to the power of about 9 million people. E to the 9th power is a big number. 34 times e to the 9th is a big number. And 1,000,000 times 34 times e to the 9th power turns out to be, well, the number we get out of the equation is 350,000, but that's in millions of people. So in the year 3000, California should have a population of 350 billion, which is clearly absurd. This nice growth at first was exactly what we wanted, but this rampant accelerating takeoff growth is not ideal. There are physical constraints like the fact that 350 billion people literally couldn't fit in California unless you piled them several people deep, which isn't conducive to a happy life. Well, what I'd like to have is a model that accelerates like an exponential function at first, and then after it hits a certain point, levels off due to constraints like not enough food, not enough space to sleep. I'd like a function where instead of an exponential going off forever, I'd like it to kind of have a moment where it comes to its senses and level off towards a maximum. So instead of this, I'd want that. The good news is there's something that works exactly like this. It's called a logistic function. It's very special in that it's going to have two different asymptotes. One down here, where as you go to the left, the further we go to the left, the closer we get to 0 without ever reaching it. In fact, on the left side, a logistic looks exactly like an exponential function. It's after this divergence point that things really get weird, because it also has an asymptote on the right. There's a maximum value that the logistic function will almost reach, but never exceed. It can get as close as you want it to. This maximum value is supposed to represent, well, we call it a carrying capacity. And what it's supposed to represent is this is the population at which not a single additional person could fit into California in this example. So what would an equation for a logistic function look like? Well, here's the bad news. It looks like this. I'm not expecting you to memorize this, but if I give you a function of this form, I'd like you to be able to do a little bit of work with it. There are 3 parameters now. This B parameter tells you how fast you're growing. The A parameter is going to help you set your initial value, and the C parameter is going to help you set your carrying capacity. So these things are a little bit more informationally complex than those very simple 2-parameter exponential functions we were working with. But this right here is how we do a logistic function. Now, let me try to explain to you what it is that each of these 3 parameters do. Like I said, B is some kind of growth rate. What's the initial value? Let's take a look at the initial value. This is going to be kind of weird. So if t is 0, then y is c over 1 plus a e to the negative, well, b times t, so 0, really. Negative b times 0 is 0. Now e to the 0 is 1, so this is c over 1 plus a times 1. So it's just c over 1 plus a. Our initial value is going to be c over 1 plus a. Now the carrying capacity is what happens when t moves toward infinity. What's going to happen there, do you think? Well, we have y equals c over 1 plus a e to the negative b times, I'm going to abuse notation very badly here. Infinity is not a real number, but imagine we put in an infinity here. Well, negative b times infinity is really no different than negative infinity. The b doesn't matter. Infinity times b is just infinity. So what does e to the negative infinity look like? Again, I'm abusing notation very badly here. What I really want to know is, if I take the function e to the x, and I take x towards negative infinity, what does y equals e to the x do? Well, what y does is that e to the x, this y equals e to the x, it's going to approach 0 as x approaches infinity. So when I take a times e to the power of negative, really huge negative number, e to the negative infinity, what I'm getting is something that approaches 0. So y is c over 1 plus a times something that's about 0, if not quite. Well, a times 0 is 0, which leaves us with c over 1, which is really just c. So the carrying capacity is c. So c is your carrying capacity, c over 1 plus a is your initial value, and b just tells you how quickly you get from one to the other. Let's take a look at a somewhat more reasonable model for the population of California. I could model the population as 95.2 over 1 plus 1.8 e to the power of negative 0.018 t. So 95.2 is my c, 1.8 is my a, and negative 0.18, negative 0.018 rather, is my b. Let's see here. What's my initial value? Well, it should just be c over 1 plus a. If I plug in 0 for t, I'm going to get just 95.2 over 1 plus 1.8, which is 95.2 over 2.8, which so cleverly does come out to equal 34 million, like we said. So the initial population is still 34 million, but now we have a new feature. The carrying capacity, well, it's just going to be equal to that number up top, 95.2 million people. So under this model, we're assuming California cannot grow to a bigger size than 95.2 million people without some drastic change in technology that allows us to fit more people into a smaller space. That's as big as California is going to get. Let's do one more thing. When will California have 68 million peeps? Okay. Okay. You might be looking at this and saying, you expect me to solve 68 equals 95.2 over 1 plus 1.8 e to the negative 0.018 t? And I'm going to say, yes, I expect you to solve 68 equals 95.2 over 1 plus 1.8 e to the negative 0.18 t. As a matter of fact, this is just an especially complicated example of socks and... Oh, snap. Google Meet has crashed. Well, I will continue this example in the next video.